Hello dear students, in this lecture we will talk about the schematic instrumentation for absorption and emission spectroscopy. The diagram that represents schematically the instrumentation of absorption spectroscopy is shown as. Here we have a light source that gives off light in all possible wavelengths. This light is then passed through a monochromator to get a particular wavelength or frequency of that light. That particular frequency or wavelength of light is then passed through a beam splitter. This beam splitter is an optical component that splits the beam into two parts. One part is transmitted through the sample while the another part is reflected. For absorption spectroscopy, 50-50 beam splitter is used. The transmitted light is then passed through sample, while as the reflected light is passed through reference by means of mirror. Detector D measures the intensity of that light. The transmitted light from the sample gives IT, that is the intensity of transmitted light, while as the detector at reference gives the intensity of incident light. Computer processes the data itself to get absorbances directly. Now, what this monochromator is all about. Monochromator actually consists of lenses, mirrors and gratting. If you can see in the diagram, rays of light coming from the light source are collimated by means of collimating mirrors. Had there been no entrance slit, then there were chances of slit ray radiation to interfere. So to prevent interference of slit ray radiation, entrance slit is being used. Collimating mirrors collimate that rays of light onto the diffraction gratting. Diffraction gratting disperses the radiation into different components of wavelengths. As you can see here, we have lambda 1, lambda 2 and lambda 3. These different wavelengths are then focused onto the exit slit by means of focusing mirrors. Here at the exit slit, it is lambda 2 that is coming out from the exit slit and hence can be used to excite the molecule. If the energy levels in the sample or molecule are such that the gap between the levels correspond to lambda 1 or lambda 3 wavelengths, then to get those desired wavelengths, the best way to choose that wavelength is to move gratting or tilt that diffraction gratting. By tilting that diffraction gratting, one can choose a desired wavelength of radiation for exciting a molecule. Such a process of choosing a desired wavelength for the excitation of a particular sample by moving the diffraction gratting, we call it scanning. Now, at the diffraction gratting, if theta 1 is the angle made by lambda 1 and theta 2 is the angle made by lambda 2. As per Bragg's law, for n is equal to 1, that is strong scattering, lambda 1 will be equal to 2d sine theta 1, lambda 2 will be equal to 2d sine theta 2. Now take the difference, delta lambda will be equal to lambda 2 minus lambda 1. While putting the values of lambda 1 and lambda 2, we get delta lambda will be equal to 2d sine of theta 2 minus sine of theta 1. Delta lambda will therefore be equal to 2d delta of sine theta. On rearranging, we get delta sine theta by delta lambda will be equal to 1 by 2 into d, where d is the interplanar spacing in the diffraction gratting. Here, delta lambda is the difference of wavelengths or the difference of signals or the difference of peaks that one wants to resolute in the absorption spectroscopy. Now, for the given value of delta lambda, delta sine theta need to be large so as to have better resolution of peaks. This is possible only for smaller value of d, that is the interplanar spacing in gratting. But it is important to mention here that diffraction from gratting takes place only provided the interplanar spacing, that is d, is of same length as wavelength of light used. Therefore, within the limit of wavelength of light used, smaller d is better for good resolution. Smaller d is not the only factor that determines the resolution of peaks. Slit width of the exit slit also matters. For example, we have a slit of larger width. Different wavelengths can pass through that slit, hence the signals or the peaks are not good resoluted. Now, when the slit width is reduced, at one point of time, one wavelength will pass through it to get one signal or one peak, and at the another point of time when the diffraction gratting is moved, that is scanning is done, another peak will arise. This leads to good resolution of peaks. But there is the problem of smaller slit width. That is, if you decrease the width of the slit, less light will be passed through, hence intensity of the signal will be decreased. That affects the light gathering power. So we can say smaller slit width may affect light gathering power, that is the amount of light collected by the detector. Once less light is collected by the detector, it leads to smaller signal and noise takes over. This leads to smaller signal to noise ratio, thereby making spectra noisy. Thus, proper slit width is needed. So we can say that to have a better resolution of peaks or signals in the absorption spectroscopy, one point to note is that D must be smaller, but not that much smaller that we don't get the diffraction pattern at all. Number second is slit width must be smaller, but not that much smaller so that we don't have much light collected, that is it affects the light gathering power. So optimum slit width is needed, number one, and within the wavelength limit of that light used, D must be smaller. Finally, detectors detect the light signal, and the detectors can be of two types. Number one is single point detectors, that is the photodiode or photomultiplier tube, and we have array detectors, that is the photodiode array charge coupled devices or intensified charge coupled devices. Now, talking about the emission spectroscopy, we know for emission spectroscopy, molecule is to be excited first. So if nu Ex is the excitation wavelength or the frequency that a molecule is excited, and in the excited state there occurs some relaxation phenomena, and then the molecule begins to emit different frequencies or wavelengths of light. Nu Em is the frequency of light emitted. Now, since the molecule is first excited, to select that particular frequency or wavelength, we use one monochromator, that is the excitation monochromator. This excitation monochromator then gives a particular frequency that is impinged on sample. The sample then emits light of different frequencies, and to choose the emission frequency, we have to use another monochromator that selects which frequency of emitted light is to be used. So in emission spectroscopy, two monochromates are used, which makes it costly. This is one of the reasons that emission spectrophotometers are costly, because of the use of two monochromators. I hope you understand it. If you like my videos, please do not hesitate to subscribe my channel. Thanks for watching DHC.